In this video, I'm going to continue our discussion on degenerate perturbation theory. And so in the previous video, we used the method where we had that epsilon that we could sort of decrease until we got our degenerate states. So we had that graph that looked something like this. We had a state where if we added the perturbation, it split this into two different energies here. But if we sort of took our epsilon, which was what we had here, back to zero, we ended up getting this point here where the energies were the same, and so it was degenerate, but it was two different states with the same energy. And so we found this as our two different states, so the plus state and the minus state. But as I mentioned in the previous video, if we could do this, then we wouldn't need perturbation theory because we just assumed that we could find the two states in the perturbed state there, and then just sort of take this perturbation away and find our two degenerate states. And so we need our degenerate perturbation theory. And so we have a linear combination of states. We have this psi A and the psi B with these alpha and beta in front of it. And so we have our eigenfunction equation here with our Hamiltonian there and our energy eigenvalue there. And so we will do just like we did in the non-degenerate perturbation theory. And so we find these orders of lambda. So we combine like orders of lambda. So that I have this dark red here and this dark blue here for our two first order corrections to this. And so if we look at just our first order corrections, so we have this with the red here, which has our Hamiltonian, and this with our energy eigenvalues here. And so we take the inner product with our psi sub A here. And so we go through the math with that, and what we find is that we have this alpha times this here and beta times this here equals alpha times our E1 here, so our first correction to the energy here. And so then we can just define these two terms up here as this W sub AA and W sub AB, and we get that alpha W sub AA plus beta W sub AB is equal to this alpha E. And then we can do the same thing when we do the inner product with this psi sub B. And so what we get is the W sub BA and W sub BB. And so those we can just put into a matrix here. And this matrix is our perturbation Hamiltonian. So it's the perturbed part of our Hamiltonian. So remember, our Hamiltonian is equal to that Hamiltonian of the sort of ideal state plus our Hamiltonian of the perturbed here. And so this will this matrix right here is our first order perturbed Hamiltonian here. And so we can see how that as a eigenfunction equation here gives us the first energy correction right there. And so the W, as I said, are the first order energy corrections. We therefore want to solve for the eigenvalues. And so we just go through the math here for eigenvalues. So we have this right here. We subtract this from both sides, we get the zero vector here. We have this times the identity matrix right there. And so we just go through that and we end up with this right here. So we have our WAA minus the energy eigenvalue there and WBB minus the energy eigenvalue there, acting on our basis vector here equaling the zero vector there. And so we need this matrix to be non-invertible in order not to just get trivial answers. And so the determinant must be zero, because this right here is how you find the inversion, which needs the determinant down here. And if that's zero, we are dividing by zero, and therefore it is non-invertible. And the reason we want that is because we want from the determinant to get this equal to 0, so then we can use the quadratic equation on it, because this right here will be our determinant right there. And so we are using that the W sub AB is equal to the complex conjugate of the W sub BA. And so we just do FOIL with these two terms right here. And so when we go through that, we end up getting this right here, which is in the it's in the form of like a second order polynomial. And so the A is equal to 1 because there's just a sort of implied 1 right there. Our B is equal to this minus WAA plus WBB, and our C is equal to this minus WAB squared. Just so we're assuming real. The values that we get should be real, and so the complex conjugate here should just be equal to the WAB, and so we can use WAB squared there. And so we can solve for the E here using the quadratic formula, because our E, which is our eigenvalue, which is our energy here, is basically the x here. And so we can just solve the quadratic equation, which is this. So we put those terms from above up there for our quadratic equation, and we end up getting this. And so that is what can be used to find the perturbed energies. And so we can find the matrix elements for our W, for our perturbation, from this perturbation that we had above. And so we just find the WAA and WBB using these integrals here, because we are just doing the perturbed Hamiltonian sandwiched between our two wave functions here. Then we just split the two wave functions so that we have this, and those will both be equal to 0. And this is true because both integrands are odd functions, and that makes them 0 here. And then we can look for the off-diagonal matrix element, which is the WAB, and so we do the same thing. We have our perturbed Hamiltonian here, that will get factored out right there, and our two wave functions here. And so we split that apart so that we have our two different wave functions there. So the 0, 1 and the 0, 1 with the x and the y in between there, because we know from our 1D harmonic oscillators that the raising and lowering operators are these, and so by themselves are these right here. And since we're interested in x, we can just add these together and then solve for x, and we end up getting this right here. And so we will actually substitute that in for our x's up in these equations up here. And so we substitute those in, and we are just squaring it essentially, because we are just multiplying them by each other. And so after we solve through that, we end up with this right here. But the integral of these two things multiplied by each other and then squared will be equal to 1, since they should be normalized. And so we end up with this right here. So our W sub AB is equal to this epsilon times h bar omega, which is our angular frequency, over 2. And if we did the same thing for WBA, we would get that WBA is equal to this as well. And so we end up with this as our matrix. So we have these 1's in the off diagonal, and then we've just factored out this h bar omega over 2 times our epsilon there. And so we will get the eigenvectors for this that are this. So this one is the 1, 1. This one is the minus 1, 1. And so, I mean, if you wanted to graph those, you could think of it, 1, 1 would be kind of pointing that way, and minus 1, 1 would be pointing that way, essentially. But we won't think about that for now. And so the linear combination will be this 1, 1 plus this minus 1 here, which are normalized with a factor of 1 over the square root of 2, giving us this linear combination. And so this should look familiar because it's exactly the same as this one that we got from our previous video here. And so it's the same one that I showed above that we got with that strategy we used in the previous video of, well, when we said we assumed we knew what the perturbed states were. In this video, we were looking for those perturbed states, assuming we didn't know what they were, and we ended up getting exactly what we assumed they were in the previous video, which, you know, we could obviously assume we knew those because you know, we did know what they were, and so we could just sort of assume that. But anyway, this and what we did here was showing that we can find those without just assuming we know what they are. And so we have the eigenvalues of plus and minus this h bar times our angular frequency over 2. We can see that, so if we act on this vector, if we act our operator on this vector here, the 1, 1, we get this here in red. And if we acted on the minus 1, 1, we get this here in red, which is just the minus epsilon times h bar omega over 2. And so these are our energies here. So if the W sub AB, which would also mean the W sub BA, equaled 0, we would have the eigenvectors 1, 0, and 0, 1, which is just the case when we can use the non-degenerate perturbation theory. So these should, you know, look familiar. These are sort of the orthonormal basis right here. So if we did threefold degeneracy, so we had 3 states here with the same energy, we would essentially just use the same strategy as above, but we would get this 3 by 3 matrix instead of a 2 by 2 matrix. And in general, in n-fold degeneracy, we'll use an n by n matrix. But we are getting this matrix here, which is the correction to the energy for if it's the sort of first order correction, it's a 2 by 2 matrix, second order is 3 by 3, so on and so forth. And so we can get the energy corrections that way. But anyway, that is sort of how this perturbation theory works. So essentially we want to get this. We want to be able to solve this quadratic equation here, which we obtained from the determinant here of a matrix with the WAA, WAB, WBA, WBB right here. And so we're doing the eigenvalues here from the determinant, which allows us to get this quadratic equation here. Then solving the quadratic equation is what allows us to get the energies for our perturbation, for our correction here. But anyway, I hope you found this video helpful. I will be talking about sort of a way that you can oftentimes find the energies that's a little bit easier, and I'll be doing that in the next video. But anyway, I hope you found this video helpful, and I will see you then.